All right, how's this for sound? Is that picking it up, Jason? All right, hey, morning, everybody. Thanks for coming out. I want to thank Brandy and Jason for the opportunity to come in here and talk to you about the hottest topic in the industry is PFAS. I can see everybody in the room here showed up to figure out what the hell does Dean know about PFAS. I don't know much, that's why we brought Nick. So I'm going to turn it over. Nick has forgot more about PFAS than I will ever know. The reason I bring Nick is you think about some comedy teams over the years, Laurel and Hardy, Abbott and Costello, even David Spade and Chris Farley. And what do you get with humor? You get fat guy, skinny guy. And so that's why I wanted to introduce Nick. Nick is with ECT2. They have different methods of removing PFAS, whether it's water, drinking water, whether it's wastewater, whether it's leachate. So it's not a one-size-fits-all for your treatment, whether it's single-use carbon, whether it's ion exchange, single-use. We're going to talk a little bit about regeneration, ion exchange media. We'll talk a little bit about side stream treatment at wastewater plants. And then the other thing we'll talk about is a little bit of foam fracking. Foam fracking is more on the landfill side of things. But if you have a landfill in your town, that might be something to consider. So I'm going to turn it over to Nick Backman from ECT2. And Nick will give us a presentation and just kind of run through and more of a discussion than anything else. So if you have questions, just raise your hand and we'll go along the way. Awesome. Thanks so much, everyone.
Great. Thank you, Dean. How are we looking and sounding? Great. All right. So I'm going to get right into it. Going to take about, let's call it 40 minutes. I want to leave some time open for questions. Dean alluded to it. We're going to lean in on a few different technologies. And what I'm hopeful that you take away here today after I'm done is granular activated carbon is one of a few different options that we can really look to evaluate here. One thing I've been kind of leaning on a lot is we really like to begin with the end in mind and then walk it back from an engineering perspective. So what do you need? What does it look like? And how do we get there? And then how do we make it the most appropriate fit, both from a CapEx and OpEx perspective here. So just getting into it, little credibility. ECT2, my company has been treating, it stands for Emerging Compounds Treatment Technologies. So we've been working on really challenging water sources. Really started with 1,4-dioxane in 2012, 2014. PFAS emerged at that time, and we were really fortunate having the Department of Defense in Australia contact us and looking for solutions. As we know, the defense sites were using AFFF. AFFF has 38% PFOS in it. So negligently, they were spraying it, more or less practicing fire suppression in the desert in all these remote places. So as a result, the AFFF ended up in the groundwater, which is a large source of drinking water for Australia. So they called us asking for any ideas on solutions and what that could look like. So this is the first site you're seeing there in Australia. We did 4 years of work there before really anything picked up in the United States. Having that kind of dry run for the US was really helpful. We built a blueprint. Now we know how to do a little bit better for states like Illinois. So a bit further on about us, we are also owned by Montrose Environmental Group. So they own 86 verticals of different environmental-based companies, air, water, and soil. We're certainly the water component of that, and we're specifically targeting, 95% of each day. We're working on PFAS. So other verticals include enthalpy analytical. I mention that because turnaround times on PFAS analytical is it's getting longer, right? So this gives us an opportunity to work directly with colleagues. We get preferred pricing in 2 to 3 week turnaround times. So as we're developing projects, doing bench tests, evaluating technologies, we can get to the end quicker with data at a rapid rate. So kind of leaning into that, in Fuquay, North Carolina, we have a treatability lab where you know, it might be a conversation of, is it GAC, is it ion exchange? Well, let's figure it out from the least cost intensive perspective first, and that would be a number of different ways we can analyze this just on the bench at our lab. Our SSCT testing is rapid small scale column testing. So what we do is we crush these ion exchange beads and we get breakthroughs in days as opposed to months or even years. With PFAS being, you know, minimal, if we're trying to get to 4 parts per trillion and we're at 8, it might take a few years to run columns and to get breakthrough. This helps us expedite that process, again, beginning with the end in mind. Isotherm is basically a yes-no test. Will the media work? If so, then we can proceed. All this we kind of create stepwise just to give you an idea of what it looks like to really analyze this. Next phase, taking it from the bench to the pilot. Certain cities are going to want to see the demonstration of the technology at their site with their real-time water. It's great to get a grab sample, send it, test it, get some numbers. But to make it more real, this is our next phase. Column tests up there would be, you know, a couple of different carbons, couple of different resins, ability to take an honest look at if it works, which one might work better. All the way down to, you know, mobilized systems here in 40-foot containment that can run, you know, 365 anywhere in the world. Then just a quicker look here. We've got a couple different, couple different sizes basically. We're running from, you know, under your sink cartridges to 8 GPM. For all intents and purposes, you're looking at softening vessels there. 8-inch diameter, 54-inch height. These are all going to go up all the way to what you're seeing here, our 12-foot diameter pressurized steel vessels rated for 125. We've got newer versions that are shorter, and I'm going to get into the reason of why that is, but carbon, resin, pressure vessel flow through. We're designing it with specific contact times specific to the media, and I'll touch on that a bit more as well. Rapid response equipment, if you've got a spill as mentioned, you've got a groundwater site we need to treat, we can certainly deploy these independent skids. Just makes it a lot easier then to set up a system, building a building around it. This helps us get to work really quickly. So just a quick outline, I'm going to touch on a couple different treatment technologies here. And I'm going to touch on it from a few different application points, right? Whereas PFAS, it's everywhere. So how do we get it out of drinking water? How do we get it out of these passive receivers, waters, out of their effluents? We're going to get into that. Cool, quick story. That was all you see is dirt. To the left is Champ Landfill in Maryland Heights, and it's actually an old quarry. So it's like the opposite, where it's not a hill building up this way. They're bringing all their trash down into this quarry, and it's a waste connection site. We're very fortunate to be treating their leachate for PFAS. So this building we built from the ground up, put a PFAS treatment system in and built around it. So I took that earlier this week. No snow there. So I didn't want to assume we all knew everything about PFAS, so I'm just going to touch on it briefly. That is a PFAS molecule, and what you're looking at specifically is an 8-chain compound. So is there a laser on this? Yeah, either way. The purple tail there is the hydrophobic tail, so that's the carbon-fluorine bond. There's all different numbers of carbon-fluorine, which is going to make different nomenclature for different PFAS compounds. The number the ones we're seeing specifically in large part are PFOA and PFOS. So that's an 8 chain right there, so that'd be one of those two. Why? Because in large part they exist more places than not. We made the most of those two, we use the most of those two. So by nature it persists, and as a result we see a lot of it. So I think we all know most of this. I'm not going to beat us on it, but where does it come from? Scotch Guard, Teflon, anything that's making, you know, even probably this shirt being like Gore-Tex has probably got some PFAS in it. Cosmetics, packaging from fast food, it's everywhere. Carpet. So as a result, it ends up everywhere. A lot of them, as mentioned, the passive receivers, the landfills, and the wastewater treatment plants, just as a direct result of it being in convenient products. So just a really quick touch on the chemistry. I've mentioned this, but it's important to understand why. The hydrophobic tail, it absorbs into things extremely well. That hydrophilic head, right? The top, this part here, that's a carboxylic acid group. The top is a sulfonate group. I mention this because those heads have a charge to them, so they're negatively charged. We take advantage of that charge on that molecule no matter what technology we're utilizing, right? So this one here, sulfonates, a bit easier to remove, but that's what you're seeing in AFFF, PFOS. PFOA, direct result is in your Teflon. So if you look at the Ohio River Valley, all the water there, we've probably seen dark waters. I would recommend it if you haven't, but that's Teflon. So it's really specific to really certain areas. That's my ringtone. All right, so just one more slide on it. It gets easier to remove the longer the chain gets. So PFOA and PFOS, they're on the EPA MCL. We are concerned about it across the board, consuming it, discharging it. You notice they're kind of down low here. I consider 6 and below at least longer chain. Pretty easy to remove with almost all technologies. When you start getting up above 6, and again, it's these harder to remove, and the higher we go, the harder it is to remove. So PFBA is a big one you're going to hear. Right here in Cordova, Illinois, 3M is manufacturing it, utilizing it every single day. And the result of that is their groundwater is contaminated and their stormwater is contaminated as well. So I'm happy to say that ECT2 has the largest treatment system in the world in Cordova, along with a few others, Cottage Grove and Decatur, Alabama. And we're doing a very good thing there with a great effort by that company. And that's removing all of these high concentrations from 3 different flows, combining them, and then treating that PFAS to a non-detectable level. So when we're targeting PFBA, it's a real challenge. And I'm excited to show you what technology we're using to get there. So just a tech review. We'll start with carbon. That is a carbon, a granular activated carbon under a microscope, right? You see all these pores. I'll give it credit. They create specific mesh sizes, 12 by 40, so the pore size is specific to have some selectivity for PFAS. So it's beyond GAC where you may have been using it for TOC removal in the past. There is some selectivity to it. That being said, it's an adsorber. So it's going to absorb everything that it likes. Sulfates, nitrate, alkalinity, chloride, PFAS. You're looking at a pretty standard flow through diagram here, lead lag design with pressure vessels. Some points about carbon that I'll make. It typically, for drinking water, we're looking at 10 to 20 minutes contact time through your vessels. So That in comparison to the next technology, you're going to see more vessels, more media. Some of its positives are its ability to remove co-contaminants all at once. So I want to jump right into ion exchange. This is our next consideration. This is where it starts to get more selective, more catered, more specific. So ion exchange is doing the same thing as carbon, adsorption, typically 6% on the exterior of the bead, but all the magic is happening on the inside. All these PFAS compounds are finding those charges we were discussing, right? So how we do this is we've got negatively charged functional sites inside of the resin. So there's all these inner matrices in the bead. You know, I used to think water came through and would flow around it and it would attach to it, but there's all these cross sites that the PFAS want to attach to because of that ability to exchange ions. So it's going to kick off chloride on this exchange site and attach that negatively charged group head of the PFAS onto the ion exchange. Now the difference here is you're going to have the ability to essentially hold this. It's like a chelation, so it's like a pincher. It wants to grab it like a lock and key. Once it's in, it takes extreme oxidative conditions, temperatures to get the PFAS to come off of the resin. That's a win. Now we've separated it and we've concentrated it onto a solids media. For most, that's good enough. So I've touched on this. Here's your PFOS. That's your sulfonic group head. It's on the resin. We've done a great thing there. The next phase, as I'd mentioned in Cordova, it was more of a call to action of we need to put a patent around a thing that didn't exist before, right? And that was the ability to regenerate those beads. So right now, up until this point, we've been talking about single-use medias. Use GAC. Once it's exhausted, take it out. Dispose of it, however, landfill, incineration, other methods. Bring new GAC in, run it to exhaustion, repeat the cycle. It's really the same with single-use ion exchange. The positives to using resin are now you're down to 2 minutes contact time for drinking water. So we've significantly decreased the need for capital equipment and media bed depths. So we've got less media, less equipment. We get 4 times more removal in terms of total throughput, and we get more effective removal, again, to that concept of selectivity, right? These functional groups want PFBS, want these shorter chains. Carbon has the ability to grab things in the order in which they exist, and typically in large part the sizes of the compounds that are surrounding it. So hitting it with regenerable media, very simple process flow diagram, influent water coming in, counterflow through the bottom, treated water out. We're going to run these vessels basically as single-use ion exchange for 99% of their lives. Upon exhaustion, there's 2 approaches we can take here. In the case of the mentioned site in Cordova, because it's upwards to 10,000 gallons per minute, the economics drove to put a regeneration facility on site. So it's a bolted on building separate from all the other equipment, and there, because of the levels, we're regenerating weekly. In the instance of drinking water, again, low concentrations, we're not regenerating but every couple years. That's an instance where I would offer a regeneration as a service. So you're going to buy all your equipment, all of your media. Once it is exhausted, I'm going to come in, take out the media, bring it to a centralized regeneration facility that's owned and operated by us. We're going to regenerate your media and return it. All drinking water approved. Certainly good for treating industrial waters, wastewaters, etc. So here we look for high volumes typically, or really high concentrations of PFAS, and the economics really start to drive favoring this technology. You're going to ask, so I'll answer it. What happens when you regenerate it? What about the reject volume? The regeneration process is a two-step process. The first is a solvent-based chemistry, strips the PFAS, any of those other contaminants off of the resin. So step one. Step two is adding sodium chloride brine concentration back onto the resin. So what that's going to do is take the Cl part of the brine and put it right back onto those empty functional sites on that resin bead, and we can just play over and over and over and over again. These resin beads are robust. They're divinyl benzene polystyrene. They're macroporous. They're made to be used over and over again. The equivalent prior existence that still happens in a lot of these resins is they're using condensate polishers at power plants, right? So condensate polishing resin is almost a filter. It's taking all sorts of impact. So my point is, in the mentioned 2018 site, we've regenerated there over 300 times, still getting 97% capacity back on the bead. So we can continue to use this thing over and over and over again. So after we've got our media set, we've still got a waste stream to deal with. Distillation is going to recover the solvent, so we're reusing that solvent-based chemistry over and over again, really keeping that cost low. Now we've got still bottoms. That's a high TDS. We've got a bunch of salt. We've got a bunch of PFAS in here. What am I going to do with that? Two options. One we call super loading. Picture 39 trains in series of ion exchange vessels to handle 10,000 GPM. It's a lot, but what we're left with is a 1,000,000 to 1 concentration factor on a small volume of very high concentrated PFAS that we load up onto 2 3-foot diameter vessels as a single use approach. So at the end of this, we've got a much smaller solids management of roughly 54 cubic feet that we'd be changing out on an event of a regeneration. So we've touched on this, just a quick overview of each carbon single-use regenerable media. The real driver here is it's typically the lowest cost of ownership, and what we're going to do is put it against a life cycle analysis to say, here's what it costs to buy it, and now here's what it costs to own it for 30 years. That's going to give us the most true assessment. And then from there, leading into what Dean touched on, foam fractionation. This is kind of flipping it on the inverse. We look at foam frac, and I think it's important to mention it here and now that a lot of companies exist that just do foam frac. A lot just do carbon. A lot of them just do ion exchange resin. So they're all doing very great things. But what that does is makes me fit a square peg in a round hole with the technology that I have that you came to me and asked for help for. If I'm only selling foam frac and you need it for drinking water, I'm happy to say that it's typically not the best technology to deploy. We've got other things that we can look at. They're going to make more economical sense for the end user. But when it does work, it is really cool, and it's just really taking advantage of physiochemistry with a big fractionator vessel. So this thing's like 8 by 15. We bring in landfill leachate, for example, high co-contaminants, right? So it's not going to do well in resin because of all the other stuff in it. If you've seen leachate, you have. It looks like melted black licorice. It's pretty intense stuff. So depending on the landfill, it may be 8,000 gallons a day. Some of the bigger ones, 300,000 gallons of leachate a day. And what's happening as a passive receiver is they'll take their leachate, either force main to a treatment plant, as you know, or we're pumping and hauling to a treatment plant. That's creating, the solution to pollution is not dilution anymore because of parts per trillion values and the ability to detect this stuff almost no matter what, right? Like 1 grain of sand in the Empire State Building, that's a part per trillion. We're trying to pull that out of water. This is a great pre-treatment step to take it from one passive receiver to another. We're going to be able to pull out with very low energy, very low chemical consumption. Let's call it, you know, in most instances, 80 to 90% of the PFAS. Longer chains, as I'd alluded to earlier, easier to remove. That stays the same with foam fractionation. The obvious, right? Longer chain, hit it with air, it's going to want to foam. I'd mentioned AFFF foam for firefighting has PFOS in it. That's because by nature it wants to be a foam. So we take advantage of that by just hitting it with air and recirculation. So the leachate's coming in from the landfill, a pit or an EQ tank, dropping down, and we're just recirculating this over and over again, and a foam column is created that goes up the center of this fractionator to this column here. And so now all of your PFAS is in a foam, and 99+% of what you treated, your effluent, goes off, and I'm going to show some data on that. So how do we get there? Same deal. Let's start on the bench. You send me some water, 700, this one was 750 gallons. We're down to, if you send me a tote of water, I can analyze it for 15,000 bucks, tell you what the end looks like. So we'll do that in-house. Next step, we're going to do a pilot on site if you want to. Those benches, we've gotten really good at being repeatable, where we'll get into a performance guarantee on that with just data from a bench analysis. Can we go from bench to pilot? Definitely, and that's what this would look like. This is a 40-foot containerized foam fractionation system. What we're really trying to do here is take advantage of comparative HRT, retention times. So I'm basically simulating the environment, getting 11 minutes each, where I would want to replicate that in my larger vessel that I'd shown, getting about 40 minutes in there. So just that 40 minutes of recirculation time creates a good consistent dry foam by volume. This pilot is something that we can, you know, trailer in, drop on the ground, run for 2-3 weeks, optimize the testing, and know what we need to do for a full scale. This is really exciting data, kind of hard to see, but I just want to point out a couple numbers here. This is your total PFAS coming in, so about 11,000 parts per trillion. But the big thing here is that 9,000 parts per trillion of that were some of those shorter chain compounds. What's happening is, if we're just looking for PFOA and PFOS, these things degrade over time in the hill and they turn into shorter chains. So it's almost like short chain soup, and you think everything's moving in the right direction, but the total mass of PFAS remains the same. Still the same volume of PFAS, it just looks different. What I'm getting at is, we decided here that we were going to remove 70% total mass. In order to do that, we needed to figure out how to pull out some of those shorter chains, which is not easy to do with just physiochemistry. So what that looked like is utilization of different surfactant additions, and we're talking like milliliters per minute, dripping in. Now the addition of these surfactants creates further separation and selectivity for things specifically like PFBS. So you took PFOS, it degraded over time, it turned into PFBS. There's a ton of it, and we got to get rid of it. That surfactant helped us get 80% out, 87%, excuse me, and that helped us reach the target of 70%. So now you're seeing, if 4 PPT is my goal on drinking water, I'm probably not getting there, right? So great technology to pull out a bulk of the total mass. so that we're not just dealing with it another different way. This is the mentioned Champ landfill. This is the full-scale site. It looks like a lot, but it's really basic. The flow-through diagram up top here, water's coming in, holding tank, runs through one fractionator and then a second. The more fractionation time, the more PFAS we're pulling out. That then goes to this tank right here. It's a holding tank. The foam breaks back down into a liquid, and we test that liquid for the concentration factors. That matters. So really, the better concentration factor we get, the less volume of actual water's ending up right here. So here at Champ, we're getting like 2,000 to 1 concentration factors. Every 2,000 gallons we're treating, we end up with 1 gallon of foamate concentrate as a liquid. Same deal here as I'd mentioned before, super loading. So that's what we're doing with the concentrate. Now all the PFAS lives here. We're running it through those 3 vessels you can see up top there. They're little 3-foot diameter ion exchange vessels. So now we've loaded a liquid PFAS problem in a large volume into a small volume onto a solids media. At a landfill, with the data that we have, I alluded to it before, but the ion exchange not only doesn't leach off PFAS, typically takes up roughly 20% more PFAS. If I were to take it out of that vessel and just loosely put it back in the landfill, not saying that's what we want to do, but if that were to happen, it's not only sequestered, but it's actually taking up PFAS all around it. So there's still some throughput capable, and it's not just going to end up where we're just chasing our tail over and over again. So that's what that looks like. Other options are taking those 3 mobile vessels, they're skidded, taking them out, and a bolt-on destruction technology goes right in on that back end. Those destruction technologies, like the things that we created, high salts and high concentrations of PFAS, and low volumes. So a company like Axine Technologies out of Minneapolis, they are using a process called electrochemical oxidation, and that basically destroys that carbon and fluorine triple bond, which is the hardest bond to break. It's the most persistent in the environment. So now we've separated and concentrated with the ability to do destruction on that back end. Other methods, while we're talking about it, of disposal for the media, I typically lean on high temperature thermal incineration. There's great reports out. One by a competitor, Clean Harbors, has 7 nines removal on the destruction and through incineration. So 99.79s removal through the air emissions of PFAS. So we're getting more comfortable with the idea that that indeed potentially can break the bond across the board. Ion exchange is actually, yeah, it's almost preferred, and it's really what I'd mentioned before, just the constituents in which it's made up of, right? It's plastic. It's got high BTU values. So an incinerator actually has to meter this stuff in because it gets too hot. So they take it, they prefer it, and we've got good data and good considerations around scrubbers in these cement kilns, like we've been doing for sulfur for 70 years. So continued path forward, cognizant of what we're doing as opposed to it's good enough for now and we'll fix it again later, right? So 100%. You're so right. Exactly. The best way that I think about that is, right now it's in the air and it spreads. We already know it spreads through rainwater. Cape Fear down in Charlotte, I'm going on a tangent here, but coming out of the Cape Fear watershed, 93 miles away is Chapel Hills University. They in Cape Fear, Chemours makes a very specific PFAS. It's called Gen X. That Gen X was the replacement chemistry for PFOA. It's just shorter, so it's less persistent in our body. It's probably a good thing. Either way, it still persists. It's only made there, so it's kind of like a PFAS fingerprint. They found it 93 miles away in Chapel Hill, just in the rainwater. So to your point, through emissions, we can find it in places where people have not been living maybe ever. So there's a reason to that. And yeah, let's not create another problem, right? So we chose a long time ago to be agnostic to the destruction piece. We're really good at taking it out, and we're really good at concentrating it. The R&D component that goes into destruction is significant. There's a number of really great companies out there, and I'm happy to say that when we make these concentrates, that's treasure to some of these folks that we're working with. Hey, here's the concentrate, here's the order and how many times it has been concentrated, here's the chemistry around it. Do your demonstrations on destruct and then share the data. So now we've got really reputable data to say these technologies work great here and here, lesser here, but helping us kind of build a full picture here with that. Last thing I want to touch on, I've got a little time, wastewater treatment plants, right? We want to, and there's no coincidence that we're ending here because everything ends here. And the best story I have is TRA Central down in Texas asking me, what does it look like to treat our 225 million gallons per day flow with carbon and or resin? That's great because, again, we're all trying to figure this out. Some states are ahead of others. I'm happy to have that conversation and show you what it looks like, and what it looks like is 5 Bass Pro Shops of carbon vessels. Significant. Roughly $198 million in pre-treatment, media, and vessels alone. And then the other side of the water's got all sorts of stuff in it, right? Co-contaminants and things that are going to make you need to change that media out pretty frequently. And in their instance, it was almost monthly. So what we're looking at here is the added scope to treat PFAS at your existing treatment plant. You know, you're probably going to need some version of RO, nano, or ultrafiltration ahead of your GAC vessels. In that case of 225 million gallons, it was 98 pressurized 12-foot diameter systems, and as mentioned, almost $200 million. So what can we do? We cannot do that. And NanoZorb is a way to take advantage of the process that you have in place already. So we're retrofitting into an existing MBR. We're taking advantage, or an aeration ditch, or an SBR, or an MBBR. So what I'm doing here is I'm adding a silo and a hopper and a media. It's a dry powder. I'm dropping it down, making it into a slurry, and injecting it in line into your aeration basin, for example. Now here, I'd mentioned before with fractionation, HRT. Here I'm taking advantage of SRT. So I'll go back there, but just the very basic dumbed down version, I'm injecting it in line, and I'm taking advantage, you know, as opposed to your contactor vessels, 20 minutes maybe. Now we're looking at, you know, 3,000 minutes plus taking advantage there. So what is this NanoZorb doing? It's essentially an enmeshment of PFAS into the biological flock. So my best example is an SBR in Michigan. It's a landfill. They've got a PFAS problem. The treatment plant gave them an IPP to remove PFAS. And we evaluated all the technologies, and adding NanoZorb into their SBR and removing it in the sludge was far and away the most economical and the most efficient. Great question. It's a landfill in this instance, so we're putting it back at the hill. We're keeping it there.
Okay, but it's got the PFAS in it.
You nailed it. Exactly. Now, it enmeshes this. And same as I'd mentioned about the ion exchange, 55% uptake of PFAS if we were just to throw these biosolids with PFAS right back in the hill. So same deal, it's got adsorptive and uptake properties. There's other options. Dean and I work with a company called 374 Water. They've got an air squo system that actually destroys biosolids. So that pyrolysis, there's other ways we can handle this. But this is the path, and what we see is it's not only, it's not toxic, it's inert. So like there's no effects on, we've done testing on various membranes to assure that the effectiveness, it's not having some counter issue to it. So it's very inexpensive. It's a consumable. So once it's in, you're using it till it's gone, and you reuse it, and you use more over and over again. The beauty we see is when we test the effluent, there's no nanosorb like left in the effluent. So that's telling me that it's grabbing PFAS and all these other things. So that's the really fun part. 1 MGD facility, here's your value prop, right? What is it going to cost to put in GAC at a 1 MGD facility? $4 million bucks. But the real number of concern here is your operating time using GAC on your changeouts. $18 million over the course of a year. Nanosorb install less than $2 million, and your consumption over and over again is repeatable, and it is significantly less. So what else is it doing? It's a great nitrifier. It's improving filterability. So you can see over time it was helping, but as you continue to use this over time in your system, it's going to continuously help improve your filterability. The other ancillary benefits, now this is all, mind you, while we were targeting PFAS, we wanted to do our due diligence and see what else it did. Did a great job pulling out COD. Does a great job pulling out TOC. So in the instance of the mentioned landfill that I'm working with in Michigan, it was almost a Trojan horse approach where their first issue was color. And they get seasonal swings of TOC, humic fulvic acids, giving them a significant color tinge in their effluent. That was an issue for the treatment plant. So we looked at the testing. We analyzed it against TOC removal, figured out it was pulling out 90+% TOC. Direct result there, drastically reducing that color impact. And then, oh yeah, by the way, it also pulled out 99% of your PFAS. You guys good with that? Great. So doing a good job on TOC. The other really great data point is 1,100 ppm ammonia existed in one of the landfills we looked at. We got it less than 1. And this again was targeting PFAS. So we understand that there's more issues than PFAS, but also I'm not trying to muddy the waters and extend and expand on the scope unless I absolutely have to. Here I can do both of those things all in one. So ammonia, TOC, COD, and then, of course, PFAS. So what we're looking at here is at a wastewater treatment plant, Anson, Madison, Maine Sanitary District. They take like 5 different landfills leachates. It's a considerable volume per day in addition to a couple million gallons of flow. So the beauty is blue dots, all influent PFAS concentrations. This is when they started bringing in the leachate. And the green dots are all PFAS removal. It's the sum of the main 6 PFAS. The state of Maine is specifically concerned of 6 constituents. They add them up. The sum of those 6, we're at essentially non-detect on PFAS removal across the board. So this is happening right now actively every day in Maine. And the real beauty here is the symbiotic win of saying, I have a municipally owned landfill and I own my treatment plant. Somebody's got to do something. What does it look like? How do we do it? In some instances, it's treating at that point source where the landfill is contributing 95+% of the PFAS. Other times, in the case of Anson-Madison, they've got a semiconductor, they've got metal platers, so a lot of that total mass is coming from a significant amount of sources. Point being, it made more sense to treat at the treatment plant in this instance, and this is what that looks like. And then, yeah, I mean, specific to the PFAS that we'd alluded to, same deal, longer chains, easier to get rid of. Last thing, and I don't have a slide for it, I apologize, but the opposite, let's flip it upside down. We don't want to impact the biosolids. Now I'm at a treatment plant, and I will use one in Michigan, 1 MGD. We're taking the WAS centrate line, which is 73 gallons per minute. We're creating a side stream where you're going to get a skid mounted system, and it's a very similar process where we're retrofitting into that side stream, making down a chemical, injecting it, taking advantage of retention time, making a solids, and then returning the centrate line. What we've done here is created a small amount of biosolids, 1-2%, which is extremely loaded up with PFAS. Now 98+% of our biosolids are going to meet those targets. In Michigan, they were at 18 ppb. If they hit 20, they now have to spread on twice as much land as before. It's a significant cost increase. We took them from 18 down to less than 5 with our first order of testing. So now they can comfortably continue to land apply in the state with a very minimally invasive retrofit into the system. And just, round order, less than $250,000 a year to do this for a 2 MGD, as opposed to what they were looking at was tens of millions to continue to land apply. So all that said, we really want to dovetail and engineer and cater whatever treatment looks like for your system specifically. So I appreciate the time. I'll stop. If anyone has questions, great. Otherwise, this is going to come out in a PDF, and Dean and I are available for you all anytime. Yeah, thank you. For sure. Anybody questions or thoughts? When it becomes an issue, let me know. Happy to help out. Any other questions, general, along the way? I got my card up here.
So Brandy, you might know a little bit more about this. You might be able to.
We're going to take a 5-minute break and we'll be back.
So I just put this in my pocket, you think?
Yeah, you should be able to just.
I can even clip it.
Just clip it on the pocket.
Yeah, maybe go something like that, I guess. Yeah, just hope I don't knock it off or anything. All right.
Just try to stay back between the clocks. That's where, like right where you're at.
Yeah.
Between the two clocks.
Okay. I like to float around sometimes too, but I guess I can't do that, right? I'll walk around the room sometimes when I do these, but I'll have to stay stationary. Okay. All right. Morning, everybody. Hopefully you got everybody in here. My name is Kevin Padera. I work for a company called Enicon Corporation. For those of you who don't know who we are and what we do, we're a manufacturer of 34 different unique polymer composite coatings, all designed to repair, not replace building structures, equipment. It could be concrete, it could be pumps, it could be tanks, it could be floors. A lot of different applications. So today, specifically, what I want to present to you guys, if you saw it, is the maximize uptime and pump efficiency utilizing advanced polymer composites. Oh, go back here. So what this was is, this is a, well, here's a study. All right, project overview. So what it was is, there was a county out in New York called Monroe County, and they wanted to do a study on all different pumps. This is on the potable water side. But they wanted to determine, all right, we're sandblasting these pumps, these components, these impellers, these volutes, but are they getting efficiency gains? The answer was not really. What happens is you blast it, you're going to be at a certain peak, and I'm going to show some charts on it. And as soon as that pump runs over, let's say 30 days, 60 days, a year, it really drops back down to where it was previously. So they wanted to determine if we were to use coating, epoxy coatings on the inside of this, not so much on the impellers, but more on the volutes and the horizontal split case, what would happen on that? So we'll talk about the findings, we're going to talk about the results, we're going to talk about the coatings, how they held up over the long term, their recommendations, and of course QOA. And I'm actually going to show a lot of real life examples after that. So here's the objective. I kind of mentioned this already. So they used it on 17 different pumps at different lift stations, different pumping stations. Again, this was done through the New York State Energy Research Development Authority. That's what that NSERDA stands for. And again, it was done with 30-day intervals, 90 days, 6 months, 5 years, and beyond. And the biggest thing they wanted to determine is, hey, we're paying a lot for running our pumps, right? In every plant, that's one of your greater expenses is your electric bill. Well, what's going to happen over time on that is you're going to get efficiency gains. You're going to save a lot on that. In addition, there could be rebates offered by utilities that could really help pay for the project, which is all the better. Go to the next slide here. So here's the problem statement. So again, you're seeing a corroded pump right here. I don't know if that looks familiar to anybody that's in here, but that was pretty shot with the rod of erosion and corrosion. You see a lot of this on some split case pumps right here. And then they're showing one that's coated on the bottom of that. You're going to get much less drag when you're having a pump that's coated on an impeller or on a volute or a horizontal split. So if we want to see, all right, we're getting a lot of our increase on our power bill. How's that affecting our maintenance costs? And then they wanted to see if the coating could reduce surface roughness and improve the hydraulic performance. That's what we're looking to do here. Hopefully that doesn't look familiar right there. The tuberculation on a pump, not really that great. And of course, you see a lot of this. You'll see erosion and corrosion in a pump volute right there. So what they want to do is pump mechanics and coating applications. They wanted to focus on pump casing surfaces. They wanted to determine the surface roughness, how it affects the flow and energy efficiency. Here's the coating application. So when you're doing that, you do have to sandblast, right? Proper preparation prevents poor performance. So that's what they wanted to do there. So they would always follow the manufacturer specification. Typical application is going to be 2 coats, maybe 6 to 8 mils thick per coat. But the key is, of course, you want to get that proper prep, because if you're just going to sand it down, you might have some issues on it, especially if you're doing the entire interior of a pump or a volute casing. So here we go, the methodology, 16 horizontal split case pumps across multiple stations. So again, they were doing this over the long term. They did test some different systems on that, my company being one of those, and they did work with some other manufacturers on that as well. So we're an epoxy Novolac manufacturer, but they did powder coat. They wanted to determine which ones were going to work out the best. And here's the procedure. So they did baseline tests. They wanted to measure flow, head, horsepower, and efficiency. And then they want to do post-coating tests at intervals. So they did open that up, and they want to see how it looked after 30 days, 90 days, 1 year, etc. And what else did they do? I'll show you the next. So the other thing they wanted to determine is, and you do this post-coating, and this is no cutting or anything. So this is tests. You want to make sure you could monitor your power, right? You want to see what it's going to be before you start the project. You want to see what it is during the project and see if you are actually having tangible savings there, which they did. So these are just really simple ways to do that. And what we can do is, after we do this test beforehand, after the coating's been applied and you monitor that over a time period, you submit that to the utility and you're going to be eligible for rebates. That's how that's going to work. So this is a pretty eye-opening slide right here. So this one has 60 horsepower pump, and this is the initial and over time. So in this case, they just did some mechanical refurbishment, did some seals, did some wear rings, and they want to see what that was going to look like with the blasting. So I'll actually come over here so you can see this. So it starts up at 80%, it goes down to 72. Well, we're seeing it on a lot of new pumps, and you put these in, your efficiencies go down to what that manufacturer curve is relatively fast. So it might be in, and it might go down. Let's say you're at 90%. Pretty fast, you're going to be down to about 80% or so. And after time, you're going to be down to 60% of what that manufacturer's initial curve is. We can see on this case here, this one pre-restoration, so they didn't do anything to this. You're running at just a little bit over 75% efficiency. Now post-restoration, look, you're coming up to 79. Not that great, but you are a lot higher than you are here. But now after 30 days, after 90 days, after 6 months, and after 1 year, you're kind of getting this again because, again, there's no protective coating applied, and you're kind of right back where you started. So in other words, it really didn't give you a lot of good evidence, a lot of good data. Now, on that same 60 horsepower pump, abrasive blasting coating. So here's an example of one. I'll get into kind of this a little bit later on. But they had to rebuild this utilizing a ceramic paste. That's what you just see up here in that area because it was just very worn from erosion. I'll have a before slide. And then this is after the coating. You're going to get a lot more, less drag on that. You'll get a lot more efficiency. So but you can see on this 60 horsepower pump, initial and over time, abrasive blasting coating pump number 2. So pre-restoration, you're sitting on this one at about 72.5%. The coating was performed. You can see you're up at 82%. 30 days, 90 days, 6 months here, 1 year, 1.5 year. You see it holds up pretty steady on this. Now you might think that's not a lot when you look at that, but 10% is a lot. It's going to save you quite a bit on the power standpoint. You're going to be drawing a lot less. The fluid's going to be flowing through at a much better rate to what your manufacturer's efficiency was when that pump was new. So here's another one, energy and lower life cycle savings. So the energy impacts. So what they have determined, again, this is an all-independent study. The study is about 380 pages, so it's a very robust study. We actually compressed this quite a bit in this slideshow, but there is a lot more data to it than what you see here. What I like about this one is you can see here, they had significant savings on this pump number 1. They showed reduced kilowatt usage, and they had a lower life cycle cost associated with the pump. So now this is the split case you can see here. This is when it was new. The coating work was done. I know it's a little bit hard to see in this graphic here, but that was in 2005. And this is after it pulled that out. This was in 2009, I believe. So this is 4 years later. This is just rust staining right here. So after they gave that a nice wash, you can see where it is right there. You might have a couple of pockets in there where maybe the corrosion did come through. But what's nice is localized touch-ups could be done and the pump could be put back into service in a relatively fast fashion. So you can see here, it held up really well. And you're going to have a lot better than having leaks, having seal issues, having corrosion. So it really does work out well to protect that split case pump. So here we go. This is another application I'm showing here that kind of talked about it previously, but you can see here where the erosion had happened. So this is what they call like a doubler plate mesh. You're trying to give it some kind of a backing because you're rebuilding that utilizing ceramic paste. That's what they're doing right here actually. So this is what it's all kind of put in place. Some pump repair facilities do this. I work with quite a few of them. This is the ceramic paste right here. They're applying that. They can always grind that down once the material sets up. And then they're going to do 2 coats of a ceramic epoxy right there for a wastewater application. Potable water, you're using generally a chemical protection epoxy. It's going to be a little bit thinner. For a wastewater application, I'd always specify a ceramic epoxy, 2 coats at about 12 mil thick per coat. That's where we sometimes will see that. It's usually okay on a volute. But when you deal with impeller, you might deal with clearance issues on that. So sometimes we're not going to do those. If we do, it would have to be a lot thinner. And I'm going to get into the study a little bit later on, I know, where we did some testing on impellers as well, just to see what the efficiency was there. And it wasn't as impressive as it was when we do the horizontal or we do the volutes. But something I wanted to show you guys here, this is just a pretty good coating system here, is where you see the compressive strength, 13,000, very strong. On a 2-component system, your hardness is pretty good there. But the biggest thing I want to show you, this isn't showing up too well, but the adhesion. That's always a big deal when you're looking at this. That 4,000 PSI adhesion to blasted metal is very, very high. What you see a lot of times when you see coating failure, wherever you're at in infrastructure, you're bonded at a rate where corrosion just gets underneath and busts it out. Usually that's around 2100, 2200 PSI. The coating is only bonded at, let's say, 1400 PSI. The math works out where it's just going to bust out. When this happens, when you have that great adhesion rate at 4000 PSI, if there was ever damage in that through erosion, through a heavy impact, rock, debris, it's not going to buckle and fail and just flake off all over the place. You might just have some localized repairs that one could do on a maintenance cycle. Maybe you do an annual inspection and you can do that and get it back up into service in a pretty fast fashion. So that was just what I need to see here. So here's the key metrics. So the efficiency results of the study, efficiency improvement post-coating was up to 15% in some cases. It all depended, and it also depends on your runtime, right? If you're running 24/7 versus running, 4 hours a day, 8 hours a day, whatever it might be here. So I'll get into this. So here's the manufacturer efficiency. So here's all the pumps that were done in the study. If you can see that, with the smallest one being 40 horsepower right here, the largest being 300 horsepower. And here's your pump efficiencies right here. So you see the post or the manufacturer is right here on this first one. You can see how it really drops down when you're in your pre-restoration. Some of them not so bad, but here on this BN number 1, the 30 horsepower dropped out a lot. On number 2, it dropped out. Some of these other ones weren't nearly as significant, but what is significant is the post-restoration efficiency. In some cases, in many cases, you're actually going higher than what you would have for what your manufacturer is having down here. So here you're running over 90% on this 300 horsepower pump. Here you're going a little bit, about the same, but again, you're right where you want to be on that. The 600 horse, you can see that was pretty high on this one. So I thought that was pretty impressive to see how that really goes right back to where you are. But look where that 40 horsepower is. That one was really down. You're only at 40%, so I'd have to imagine that was pretty eroded and corroded. And after the work was done, they weren't quite there. But they're, of course, they're still sitting over 70%. The pump's going to run a lot more efficiently. Here's on the impeller. So you can see it's a little bit hard to see in the slide, but you can see the efficiency after mechanical refurbishment. That's going to be the dark right here after the sandblast and coat. And you can see the red, that's right here. So on this 30 horse, we did see a little bit of efficiency increase. Same thing on the 75 and the 75 here and the 200 horse. So it's only 4 out of, I believe, the 17 pumps that they ran this test on when they were coating the impeller of what they were seeing on that. What I've done on impellers more from a personal standpoint is they just get chewed up, they get eroded and corroded, and repairs have to be made. The biggest thing that you guys know being in the industry is you might want to get a new impeller. You might even have the budget to get a new impeller. The problem is, can you get the new impeller? What's the lead time, right? Lead times on these could be 20 weeks, 12 weeks. And then you ask any guy, in your field, you say, when do I need it up and running? It's usually now, right? Or today. And sometimes it's not possible because you just can't get it. The repair is a good way to get that up and running and get yourself back in business. And it's going to be a lesser cost as well, and that's the biggest thing. I think this is a pretty eye-opening slide, too. This one will really show a lot because this is going to be over time. So this is on the 60 horsepower pump, the initial and over time, the sandblast only versus sandblast and coat. So you can see here the sandblast only on this pump on the 60 horse. So before it was done, you're at 75.4%. Post-restoration, you're getting up to 78.9. Not really that great, but you're running a little bit better in the pumps in service. Well, here you see after, 30 days, after 90 days, after 6 months, and after 1 year. So 1 year is right here where you're at 74.8. You're not doing anything. So in other words, you've spent that money to get that sandblasted, maybe even did a little bit of mechanical refurbishment, replaced some seals. It's really not going to hit that well. Now, if you're doing sandblast and the epoxy coating, so your pre-restoration on this one was 72.6, but you can see here, you're going over 10% or right around 10%, 9% on that, and that's over time. So you can see they opened that up, inspected things after 30, after 60, this one here 90 days, this is 1 year, this is 1.5 years here. And again, the test went over 4 years on that, but the numbers remained very steady on that. So I thought that was a pretty impressive slide there to show it. And again, this is all immeasurable, this is all tangible, this is all things that you could read yourself. So now here's one of the bigger things now. So you say you get that done, there's an initial cost on it. Well, what are you saving on that? So we wanted to run the test, or they did, on the 300 horsepower pump, so a pretty large one. This is the energy efficiency cost calculator. So Continuous service, and this is assuming 24 hours, 28 to 30 days a month. So obviously this pump's running quite a bit. But you can see here your pre-mechanical, your monthly cost here, so what your kilowatt demand is. And remember, this test was actually done, this data is from 2009. If you're going to extrapolate that to today's standards, you're probably doubling it because of what the kilowatt per hour is. So you can see here, your monthly cost here on this 300 horse pump was $14,523. It's kind of a lot, right? But I mean, this is a big thing in these plants is your electrical draw. But you can see here, there's a kilowatt demand. So now we're going post-mechanical. Your monthly cost here did go down, so it's at $13,732. So what is that? About $800 or so. But now if you do here, your monthly cost post-casing coating, your head's going to be pretty similar, a little about the same. The flow is flowing better. You can see here it's 6,007 versus your pre-mechanical 5886. The hours are about the same. Your kilowatt demand cost right here, pretty much the same. But the biggest thing is your monthly cost right here being at $13,221 versus $14,523. So you go that over a year, over 2 years, over 3 years, you're saving a lot of money right there, right here. So where you're saving $1,302 saved per month, over $15,000 a year. Not bad, right? We'd all take that if that's money that we could put back into our budget. So here's the meat and potatoes of the study. I think I might have another slide that might have that in a little bit more blown up. But what I wanted to show you here, so here's the restoration costs, the energy savings, and more importantly, what were the payback periods for that county. So you see here on the 600 horse, your restoration costs. Again, this is going to be a little bit greater because this was done back in, about 20 years ago or so. But it's going to all extrapolate the same. But the biggest thing is here on this one, actually, the Behan one, that's why I highlighted that. So this one, the 300 horse, they had spent on the restoration project a little over $8,000. Their annual kilowatt savings is $163,000. So they're 24/7. That's assuming the pump's running 24/7. I know many plants aren't going to run that way. But you're at $15,632. But the biggest thing is what your 24/7 energy payback is, being 0.52. So, people in plants, data centers, wastewater plants, water plants, you're all searching for greater uptime, more efficiency gains. This is a great way to do that. And what the biggest thing is here, you can see at the totals. So for this project right here, the restoration total cost was $104,000. Their 24/7 annual kilowatt savings was over $1 million. Your 24/7 energy savings is $122,000. And again, this is all assuming that 24/7 runtime, you're at 0.83, which is still pretty good. I think any of us in this room would say if we could complete a project and get paybacks in under 1 year, it's a no-brainer to get that project done. You can see here it all depends on the horsepower, what your savings is going to be. So on this one here, the 200 horse, yeah, it took over 2 years to do that. On the 60 horse, it took almost 3 years to get it. But on some of them, you are under 1, and that's why I wanted to average that out. So you can see it's under 1 year on the average of all of these different pumps and all of different sizes. So this is kind of a blown up of the study too, just to show how that is, if you guys couldn't see that on the previous slide. So this is all of them, but I think that Behan one was pretty impressive right here. You got the energy 24/7 payback in 0.51, and again, savings over $1 million. We think that's pretty impressive. So now here's the energy efficiency losses after 5 years per pump per facility. So again, just kind of extrapolating that into some different industries. This would be at a data center right here. So the pump was newer, running at 75%, and then after 5 years, you're down to 67.5. Here's a district cooling center, starts at 80 down to 72. Now this would be more applicable to you guys, a 200 horsepower pump at a water treatment facility. Your manufacturer efficiency being at 80% right here, and then after 5 years, you're down to 72%. So not great on that, you're losing 8%. But here's your kilowatt savings per pump per facility. So we like to show this at a 5% savings, just at 5%, and at a 10% savings. So maybe the 25 horse, not great, but when you go up here to your 200 horsepower at a water treatment facility, 88,070 kilowatt hours versus 176,139. So that's your annual kilowatt hour savings per pump per facility. If big facility, big plant was going to do all of their pumps, that's pretty good savings that you see here. Even at the 5%, is not too bad there. Let's go to this one. All right, so the summary of this study was that coatings do significantly improve pump efficiency and reduce energy costs. The impact, potential for substantial savings from having a pump efficiency coating program in place with additional avenues to have projects completed through readily available utility rebate programs. So what's the next steps? We have to educate people on the benefits of pump efficiency coating program and help them navigate through utility rebate programs for maximum cost reductions. And that's going to be a paradigm shift. I know a lot of people are in charge of writing bids. You're going after the lowest price. Obviously, this is going to be an upcharge on that, right? You just can't, have that for the same price. So it's just about shifting that. I know in Monroe County, where the study was done, they do give some rebates to the contractor because they're going to get those rebates from the utility. So they're going to be able to pass that along so they can kind of adjust the bidding methods for that. So that's what we're trying to do with some of these different utilities out there. But we're definitely seeing it. The data's there. It definitely saves plants a lot of money on that. So the recommendations from the study from the engineers were adopt coatings, work with a reputable manufacturer that provides the highest adhesion rates and field service capability. It's very important, obviously. Leverage rebates. Work with utilities, which out here is going to be ComEd, and engineering companies to help offset the initial project costs. And then maintenance, regular inspections to monitor coating and wear. So now I'll get into some projects here when you're coming on pumps, just to kind of walk you through some of the process on this. So this is a conventional or unconventional repair. So you see a lot of erosion again on this impeller. You see it blowing up right here. So again, they can get the specs for the pump. They want to make sure that they get back to where they originally were, but they're going to rebuild that utilizing some mesh or a backer plate. Now see, it's all riveted in here. It's all in. It's pretty tight. Then they're going to encapsulate all that with the ceramic paste is what they're doing. So they're rebuilding those veins essentially. Then they did. In this case, most applications that I specify, I would go with 2 coats. In this case, they actually wanted to go 3 coats. So they had a base coat blue, middle coat gray, top coat blue. Well, why is that done? Well, that's going to run over time. Yes, there's going to be some erosion. It could be considered sacrificial, right? So what you want to do is you could open that up on a maintenance cycle. I see that blue there, and then I might see the gray exposed. Oh, that's an area that I might have to do some touch-up work. Or if it's all one color, you're not going to know that until it's down to the original substrate, to the original metal. So that's why you always want to do different colors on that, just so it really simplifies, A, not only the touch-up work, but B, whoever's doing the application can know what they're overcoating, right? Impellers, you have a lot of tight spots, a lot of corners, a lot of edges. You might miss some spots, so you just want to make sure you cover everything when you're doing that. How about this one? So this was a really interesting application. This one had come out of Europe, but this was one that was done in 2009. You can see that impeller was pretty shot, a lot of ragging going on, a lot of erosion, corrosion happening. So after they blasted it, most people would say, that's shot, we got to replace it, but not necessarily the case there. So in this case, they welded metal to that pump impeller, again, to give it that backing, and then they're going to encapsulate that with ceramic paste. You'll see here. So that's the ceramic paste that they're encapsulating that whole pump in, more or less, just to rebuild everything and get that up to what it was originally. Because what happens is after this material cures, it's relatively simple to sand or machine or grind that down a little bit to get it all back and smooth. Now they're going to do 2 coats of ceramic liquid right here, gray and blue, and coat that pump and get it back up into service. What I like to see is after this is running 10 years in a wastewater plant, they pull that out, and a lot of that's just some staining, wash that off. Might have been a little bit of touch-up work to get done, but the bottom line is the impeller is still protected, and that's the biggest thing, right? That's where your money is on that component. The coating's going to be minimal compared to that. Here's just another impeller coating right here, so that was done. Here's an internal casing coating. Sometimes you rebuild those to cut water, so rebuild it with paste. Here's a large column. I don't know if you have anything like that in some of these plants. That's a pretty large one here. I think that was saltwater corrosion was the biggest deal. But again, getting that into a shop and sandblasting and coating that works out pretty well and protects that for many years. How about that one? This is kind of a smaller one. You might see this in some plants. So a lot of erosion on these leading edges. Really bad, probably done from impacting over years. You'd think that impeller shot, but not necessarily the case. So here's where the paste is in this one. They're rebuilding that again, a lot more effective than, you can't even weld on something like this, so that's why they're utilizing the epoxy paste, and they're going to coat it after that, and that's what you're seeing in this photograph here. You can get that up and running once again. So water plant, you deal with that. You got to get an NSF approved system, which there's plenty of those out there. In this case, they did 3 coats on this split case pump. But again, they'd sandblast that. We always say white metal finish, 3 mil profile. Most contractors would know exactly how to achieve that. It's going to be done through abrasive blasting though. That's how we will get those done. And there's another impeller, so they're going to do a couple of coats. On that one, I'd probably specify 2 coats, 6 to 7 mil stick per coat on that, and get that up and running. And again, in this case, I'm not necessarily after efficiency increases. I'm after just protection, just getting that up in service and protecting that from erosion and corrosion. Here's another housing right here. So again, coating all of that. So that's the white, that's their base coat. Top coat being a gray, and they can put that up in service. And again, that component's going to be protected for many years to come. Here's another one. This was previously coated, but the old epoxy is kind of failing, coming off, so they wanted to redo that. And then they were able to recoat that. I know it's a little bit blurry, but that one worked out pretty well too. How about this one? Valve from water plant. Look at this. Look at that one. Really bad corrosion. So they had to blast that one for a while. And you see they coated it, and there's some rough ridges on there, but they were just trying to blast it and get it up and running. I would most likely want to use some paste and refill some of that if I could. So that one. This is a kind of an interesting project here. So this was a vertical column pump. It came out of a water plant, but again, you can see a lot of corrosion on this thing. So they got the quote for $85,000 to get a new one, and of course that wasn't in the budget, so they were trying to explore other options if they could do a repair on it. So we'll see what they did here. So again, getting it sandblasted, you see the theme there. You definitely got to get the good preparation on it. But once they're doing that, you see a lot of like pitted metal. It's worn away. Right here too, you can see how the interior is pretty eroded, but you want to get that rebuilt or machined out. So what they do is they use the metal paste. So they're using this application tool, smoothing all of that out, rebuilding the interior of that, smoothly getting it nice to back where it used to be. More picture. You see this is after they kind of sand that down after everything's set up. So that's a machinable paste is what it is. People are familiar with like a JB Weld. This is like the, I'd say like the Mercedes-Benz version of that or the Maserati version. It definitely is going to be a lot more durable than what JB Weld is or like Bondo is, something like that. This is what the military is going to be using. So 2 coats of epoxy for labor and material is $75,000 less than what the replacement is. I should have put a K there, but you'll get to how it looks afterwards. So they did that for about maybe $10,000 for labor and material. But again, getting that done for much less than what the replacement cost was, and again, getting that up and running a lot faster than what it was previously. How about a impeller blade? Here's another one. You got a lot of erosion on that. You'll kind of see it here. That leading edge is starting to get eroded out. So it's either, what do? You either repair it, replace it, or you put it back into service and you hope for the best. And I know sometimes you have to do that, but it's always going to be better to do that repair. So you can see a lot of erosion on these leading edges right here. So you rebuild the veins and the blades with epoxy paste. You kind of see the theme that I'm going with here. So there's the applicator. It's kind of using his finger to get in there. You try to do whatever you can sometimes. What's nice too is when I'm looking at any of these products, especially when you're in an industrial environment, I like to look at 100% solid epoxy. What does that mean? That means there's no solvent and there's no VOC. Very safe to use, not flammable, no respirators needed. It's a lot easier for the guy doing the application. Yeah, you want to try to avoid getting that on your hands. You can get it. I've had plenty of it. It's going to wash off after a week, but you'll be all right. So here's the cured material ground down and smoothed after 24 hours. So yeah, they let that paste get nice and cured, which typically a day. Because remember, a 2-component product. So what happens? You're going to mix it up. It's going to generate some heat, and then it's going to cure. It's going to cure out. That's what happens. So it gets hot, and then it's going to harden up. So they're going to let that cure for a while. They let it cure for a day. That's going to be a pretty much full cure at that point. You might not be ready for chemical immersion, but you're good enough to get that sanded down, and then you don't want to coat it after that. So here's the 2 coats of epoxy for the wearing surface. So yeah, a little hard to see here. That was a white one. That was in a potable water plant, so they wanted to use a product that was going to be NSF certified. There's that. So there's another picture of the impeller there. And yeah, that just about concludes my presentation. I know I went a little bit short. I could go a lot longer on that. The study, like I said, is 381 pages, but I didn't want to put you guys to sleep. Any questions on anything about? Yeah, there's different products out there, but I do have one that is approved, but there's other ones too. Wastewater I'll typically do with ceramic because that's going to be a lot better for wear, but that's going to be for the wastewater. You had a question over there. It's going to hold up very well, depending on the substrate, right? If you're dealing with like a stainless steel, I typically not going to specify coating for that because it's just not going to corrode, right? You're not going to see the chemical attack. You might see some erosion going on there. But it's going to last just as long as what the original substrate is, provided it's not like a titanium or anything. But typically what I see is, cast or carbon steel, and it's going to last just as long as that. Eventually, impact might be the biggest issue on some of that, but then again, localized touch-ups could be done. Go ahead.
So you've got good adhesion where to for like bronze and
Yeah. As long as the prep is good. So yeah, you could test for that. They have something called test deck strips. So like, for example, we do a lot of chiller work. So you get a heat exchanger or a chiller. This is what the Constellation plants do out here. They'll use the ceramic epoxy on that. And what they'll do is they'll use a test deck. So it's like almost like Scotch tape, and you use a tool to kind of rub on it. Yeah, you've probably seen that, and then you test it to make sure that your mill profile is the right way. And so we'll test for that, just to make sure that we do have the optimal prep. Because you're right, if you're not going to be at that 3 mil profile, you're losing adhesion. And the worse the prep is, the worse the adhesion is going to be, the more likelihood there could be a failure. So you just want to make sure that you get that optimal prep if you can. Go ahead.
Is it your epoxy or Veronica's epoxy?
Well, I like to say it's my epoxy. Here's what I'd say. You got to compare apples to apples, because you're right. There's a whole lot of epoxy manufacturers out there. And know what I liken it to? It's like going to a metallurgist and saying metal. Well, how many different types of metals are there? What kind of alloys are there? What kind of strengths do they have? So if you're evaluating any system, just make sure you get that technical data sheet. Of course, there's a little bit more to it than that, but the bond strength is really a big thing on that, and compressive strength. But bond on a fluid flow component like a pump impeller or a volute, you want to make sure you get the best, right? It's another good example I had is, you get your dentist, right? You're getting a root canal done, and he's in there, he's doing all this work, he's getting prepared, and he gets some of that resin. He's about to put that in your tooth, right? And right before he's going to do that, you never ever stop him and say, Doc, do you have anything cheaper? You want to use the best that you can because you don't want to be in that darn chair again. So, it's kind of like that with epoxies. I would try to keep it to a premium level because it's going to work out a lot better. Because the cost, it's going to be a little bit more on the initial end. But, on any project like this, your bigger cost is going to be the labor. It's going to be the application. Yeah. Yeah, so full disclosure, I work for a resin manufacturer. Got 34 different products. I know some companies have, a very wide range of materials. They might have hundreds of different products, some of the larger manufacturers out there. But no, we're kind of a smaller one. As a matter of fact, since I'm here, I actually have the sample of the ceramic just so you can see what that looks like. So on that sample that I'm passing around first is going to be the blasted metal. That's what you're seeing there. And then it's the gray coat and the blue coat. So that would be our two components that we'd specify for a pump repair application. That's what I typically would work with when it comes to like a wastewater application, even chillers, things like that. But then we also have other systems for tanks. We'll do that, or cooling towers, potable water, whatever it might be there. Yes, Brittany. Yeah. Yes. Well, so one of the big things we do as a company is we work with manufacturers of chillers, HVAC components, and we'll do those on the factory on new components. So they want to do that. And when we do that for them, we'll say, okay, on this coating, we're going to provide you a 5-year warranty. And these can get shipped all over the globe. So if we ever have any issues with that, we'd have to send technicians out to repair that. On these chillers, we'll do, 48 high builds a year. So that means we're doing 48 different chillers, right? And they're going to UAE. They might be going to O'Hare Airport. They could be going somewhere down south. The factory for JCI, Johnson Controls, that's in San Antonio, and there's an operation in Durango, Mexico. But we do those on the new. Now, it's not on every single new one because, again, whenever the client's getting that chiller, they're going to have to pay for that. But to your point, Brandy, there's Xylem is a big manufacturer of pumps, and that's one of my good clients. So they have some new components, and they are getting those coated right out the factory for brand new because they know that it's going to provide a value to that client if we have that protection right from the onset. And it's certainly going to be cheaper because now I'm not worried about rebuilding components. We're just coming in there and doing the 2-coat application. There's some pretty large components that we're working on now for Xylem. It's for the Corps of Engineers. It's some big stormwater pumps, but they want to get those coated before they get them out there. It's pretty thick metal, but they want to protect that from erosion and corrosion just from the outset because they know it's going to be a lot better value down the line. But that's a really good question because, we're working more and more with that. Yes?
The costs in the study, was that just the extra cost to put
I think that was, yeah, the total cost, like the whole rehabilitation cost on there.
Like only a portion of that is actually the coating.
Oh yeah,
Okay, so
that's labor too.
even more of a savings then, 'cause like your coating's only smaller.
Oh yeah, it does. Yeah, it'll definitely extrapolate a lot more. That's what we're saying. You know, at 20 cents a kilowatt hour, I mean, it's double what I was showing in those slides right there for sure. Because yeah, the labor is your biggest expense when you're looking at all that. Because some of these are pretty small components, so you know it's not a lot of product. It's just going to be mostly the labor to do the install, and you know the startups and things like that. Yeah, around there, yeah. And I don't even think you used it all either. Yeah, that's just one of thousands of examples we really have all over the world on doing different things. The bigger the pump, the more savings is going to happen. But volutes are a big one that we'll do a lot of. And then, yeah, impellers here and there. I just got done with one for Downers Grove Sanitary District, so I had somebody do the application. They actually wanted me to do it. So I have guys that I've trained, companies that I've worked with, and I brought the impeller to them. You know, they sandblasted it and did the application. And then, you know, I made sure it was all good and got it back to them, so they'll be up and running. But the biggest thing again is the downtime, right? That's always the biggest thing in your guys is you need things running a lot faster. I know lead times can be pretty long. I know even if you wanted to get that one, Brandy, it was probably months, right, before you could even get the new one, you know, to your plant. Any other questions on anything? I've got cards there, so if anybody needs any of that, you know, feel free to grab one or just, you know, grab me afterwards. I'm here. So yeah, there's the references on the study. Like I said, if anyone needs it too, it's all online. I could send that to you guys. But again, it's a pretty large file. I think it's, like I said, 381 pages. It gets very, very detailed on that. So I was just trying to give you guys the synopsis of it. But yeah, there's, I conclude. So thank you very much for your time. I appreciate it. And anyone questions, let me know. Oh, I get a round of applause.
That concludes today's presentations. Thank you.